Today is the third session of day 4, and today we have Dr. Deepti Marathe ma'am with us, who is the Associate Professor and Department of Polymer Engineering, MIT, World Peace University, Pune. She'll be delivering the session on testing of composites and case studies. Thank you, ma'am, for accepting the invitation, and I hand over the session to you now.
Yes. Thank you, madam, so much. Thank you for inviting
Thank
me.
you.
Yeah. So my presentation, I have shared it. Can you see it?
Yes, I think you just have to do a full screen.
Yeah. I'll do the full screen right now.
Yeah, it's is visible.
Yeah. So you can see it? Full screen?
Yes, ma'am.
Yeah. Okay.
No, I think it's still not the full screen.
Check it.
Yeah,
I have
actually.
made it already full screen.
Yeah, now it's done. Now it's done.
Okay. Yeah. Okay. So good afternoon, everyone. So you have had wonderful sessions on the mechanics of composites. So you have seen stress tensors, then you have seen macromechanics, micromechanics, failure theories, classical lamination theory, manufacturing of composites, radiation application of composites. So you have had wonderful sessions on composites. Today, in this session, I'm going to deal with the various test methods of composites. So basically, I will first try to highlight what is the need for characterization of composites. For characterization of composites, what are the properties which are essential? And therefore, then, how do you do the tensile test properties, compressive, shear properties, spin bearing properties, and then understand a case where if I'm testing a laminate, the failure of the laminate, and how does the laminate fail ply by ply, and how you are going to characterize that. That is how I'm going to go about in this session. Now, again, I will go back to my scale of scrutiny, and then how am I going to actually do the testing? So, if I see the first zone over here is making of laminas and converting them into test specimen, or making of laminates and converting them into test specimens and then trying to find out their properties. Now, when I come to know this, I make a laminate out of it. And when I make a laminate out of it, then I test the laminate for its certain properties. Now, when I know the properties of this particular laminate, what I do is I try to make some structural elements out of that laminate. So what are the structural elements that I try to make out of that laminate? There can be beams with different support conditions. There can be trusses, and there can be so many other structural elements. Now these structural elements are then going to be a part of a product, final product, say like a car, a plane, simple applications. So the testing, when I'm going to test the product, your testing with the test specimen, the laminates, is mainly going to focus on static methods of testing. While as when I move to structural elements like beams and the larger structures, for them, I'm going to use test methods which are dynamic and which are going to correlate more with whatever their applications are. So in today's session, I will be basically focusing on the basic or the bottom of the pyramid, that is the test methods that are used for testing of coupons or tabs to get the fundamental properties of the laminate. Now, what is the need for characterizing a lamina, or what is the need for characterizing a laminate? So basically, now you have seen in all the previous lectures that stiffness or compliance matrix are determined only when you completely characterize the lamina in tension or compression. So you know that there are, for an anisotropic material there are 21 constants, for orthotropic there are 9, transversely isotropic 5, and completely isotropic only 2 engineering constants. And it is better to get the values of these engineering constants and then convert them into the your stiffness matrix. So we are going to focus on trying to understand or finding up of these engineering constants. So if I want to characterize a laminated structure made up of number of orthotropic or isotropic lamina. See, specifically I am talking about orthotropic and isotropic lamina. Then what are the properties, or what are the stiffnesses that I have, or what are the values that I have to look for? I have to look for E11. Now by now you know what is E11. Moduli in the longitudinal direction or fiber direction. E22 is the moduli in the transverse direction. G12 is the shear moduli, and mu12 is the primary Poisson's ratio. So I need to characterize all these moduli, and what I need to characterize is tensile strength in the longitudinal direction, in the ultimate strength in the transverse direction, compressive strength, compressive strength in direction 1, that is longitudinal, in direction 2, and the shear strength. So these are the moduli, and these are the values of strength that I need to characterize, or I need to understand, so that once I know all these properties, I can use all these values further for designing of the composite. This is an example of properties of a unidirectional carbon fiber composite. Why I have specifically included this? Because you can see that if I try to get the moduli, there's a great difference between E1 and E2. By now you are aware why this difference between E1 and E2. E1 is the moduli in the direction of fiber, E2 is the moduli in the transverse direction. G12 is the shear moduli. Now these are the strengths in the compressive and in the tensile direction, in transverse as well as longitudinal direction. So you can see that there are wide differences in the strengths which are going to be there in the transverse or the longitudinal direction. So for all of this, we need to do the test specifically for, as I said, tension, compression, shear, in-plane shear properties for characterization of the lamina. So then what are the important tests? As I've already said, for characterization of the lamina, I need the tensile test, I need the compressive test, I need the shear test. Now there are some tests which are kind of done as what you call them screening or quality assurance tests, meaning that these tests are carried out for kind of confirming certain properties of the lamina or screening that lamina for a particular application. So such properties are 3-point, 4-point bending, or it's called as a flexural test, then interlaminar shear test. Then there are some specific properties which are going to be application based. So application oriented tests, for example, it's a pin bearing test. So if I'm going to use these composites as a structural material and I'm going to fabricate, say, furniture, panels, etc., then during the fabrication, there are going to be number of fasteners used. There are going to be holes drilled into the lamina to fix number of fasteners together. So in order to understand the behavior of the lamina and the laminate, when holes are drilled, fasteners are put in, and they are loaded in various directions, I am going to do the test which is called as the pin bearing test. So these are few tests I will cover in this particular session. Now, very importantly, you know that in or on a micro level, composites are inhomogeneous materials. Now, last time also during my micromechanics lecture, I gave you an example of bhed. So I told you that the taste of the bhed is going to depend on each of these its components. So they are your murmuras and your imli chutney and all the other your your onions and everything. All of this together is going to make the bhed. Now, even though while eating it, I will consider it as a macroscopically homogeneous mixture, but on microscopic level, it is going to still remain inhomogeneous. So my ideal mixture is going to be that if any small amount of mixture I take, that is any small amount of beer I take, in that the proportion of the ingredients are going to be in the same proportion as I have added into the big container for making it. But usually that is not possible. I cannot go up to such great proper levels of mixing. So there is inherent inhomogeneity in the composite material. So if there is going to, I am going to make the composites by various different methods. Say you just in the previous lecture tried to understand what is pultrusion and the other methods for making of composites. Now, if I do not have all the glass fibers or all, the other additives into the composite well mixed, then I'm going to get pockets of I'm going to get pockets where there is greater concentration of a particular additive and lesser concentration of the other additives. So there is a great inhomogeneity, and this inhomogeneity actually makes the properties of composites which are statistically dependent. Now, because of all of this, I cannot go in for normal distribution to give me a realistic estimate about the properties. So what do we usually do? Say if I've decided to carry out tensile test for some metal, or if I'm carrying out a tensile test for say some polypropylene sample, I take 5 or 8 test specimen. I get the values of tensile strength and tensile modulus. And what I do, I take an average, meaning that I assume normal distribution. I take average and I report average and standard deviation. In case of composites, it is seen that this normal distribution does not give me the correct properties or the right idea about what their properties exactly are. So for that, I will use something which is called as a two-parameter Weibull distribution to understand those properties. Now here I have not gone into the details of what exactly this Weibull distribution is, but I thought I should indicate it to you that normal distribution may not suffice the need of characterizing the properties of the composite. Now I go on to the first test method, the tensile test method. Now all of us have sometime or the other used the tensile testing machine, and we have kind of carried out tensile tests for various different say metals or polymers. So we know that the specimen is of a particular size and of a particular type. And then there are certain properties which I can get from this particular tensile test method. So in case of composites, I'm using the ASTM D3039 method. From that, I'm going to get E1, which is the longitudinal modulus, E2, which is the transverse modulus, mu12, which is the major Poisson's ratio, mu21, which is the minor Poisson's ratio. I will get the tensile strength in the longitudinal direction, the tensile strength in the transverse direction, and I will get the strain in the longitudinal and in the transverse direction. So with this tensile test of ASTM D3039, I am going to get all these kind of values. So for these values, getting all these values, there's a particular method or there's a particular way in which I'm going to make the specimen. There's a particular arrangement of the specimen. So this is the specimen geometry which is shown to you in the figure. I am going to have a laminate which is a 0 and 90 laminate. So I am going to have 0 laminate for determining E1 property. I will have for transverse tensile laminate which is going to be made from 90 degrees plies there. By now you know what is 0 and what is 90 plies. With certain geometry, the ends are going to be tabbed. So here I have the details of how exactly I'm going to make the specimen. The ends are going to be tabbed and an adhesive is going to be applied between the specimen and the tabbed ends. Now why am I going to tab the ends? Naturally, I know that the specimen should not crush in the jaw due to the force of fixing the specimen there. So naturally, I'm going to tap those ends and then I'm going to mark a gauge length here in between. So also very importantly, what is going to be the rate of pulling? So very importantly, in case of composites, the rate at which the jaw movement takes place is very low. That is called as the crosshead speed. And the composite is pulled or the sample is pulled at 2 mm per minute. Also, to measure the strain, there are going to be transverse and longitudinal strain gauges which are going to be fixed within the gauge length here on the sample. Now what I'm going to get through this is, if I'm going to do a tensile test for a longitudinal specimen which has got all the fibers, so here all the fibers which are aligned at 0, I'm going to get E1 and I'm going to get E11 and I'm going to get mu12. How will I get mu12? I will get mu12 wherein I am going to put in strain gauges to measure the strain in the longitudinal direction and also to measure the strain in the transverse direction. So from the basic definition of Poisson's ratio, I am going to get the value of mu12. Similarly, if I am going to use this 90-degree specimen, here also I am going to put in a strain gauge which is going to measure my longitudinal strain. Also one more strain gauge at 90 degrees, which is going to measure my transverse strain. From that, I am going to get the minor Poisson's ratio. So from the tensile test, I am going to characterize the specimen and I am going to get the values of E1, E2, which is longitudinal and transverse Young's modulus. I am going to get the values of Poisson's ratio, which are going to be major and minor Poisson's ratio, which is mu12 and mu21. And I am going to get transverse and longitudinal tensile strengths and transverse and longitudinal strains. Now, I am aware that also there are going to be different combinations of your resins and fibers, and therefore for different combinations of resins and fibers, naturally I can get a set of values, so I can characterize the E1 and E2 from that. This is about the tension test. Now this was about the tension test where I have specimens specifically aligned with the fibers aligned in 0 degree and with the fiber aligned in 90 degree. But these are not the only composites that I make. I make composites which are not only unidirectional, but there is some off axis also. So say I have a laminate which is a plus minus 40, plus minus 30 laminate with number of layers there. Now, by now you know that whenever there is going to be some angle in the laminate, then naturally I'm going to have the values of S16 and S26. So whenever S16, S26 exists, this you have studied in the lecture in macromechanics, whenever these two values exist, then there is going to be a coupling between extension and shear deformation. And with this coupling that is going to exist, there is not going to be just pure extension of the sample that is going to take place, but there is going to be some bending and twisting of the sample that is going to take place, which is going to lead to completely non-uniform deformation of the sample. So if I have to take care of this non-uniform deformation of the sample, then I have to take care of this twisting and bending which is taking place. So if I need to get a true value of the modulus, then I have to take into account the S16, S26. So I find a correction factor, which this is the particular formula given in for the correction factor. So this correction factor helps me in getting the true tensile value for an off-axis specimen from the experimental value, so that the effect of coupling between extension and shear can be taken into account while testing the specimen. So the previous test was focused on two unidirectional specimens and giving me values for specimens which are unidirectional, either 90 or 0. But in this test, I can use the off-axis specimen and then I can use this particular correction factor and then I can get the true value from the experimental value. Now the next property or the next test that I'm going to discuss about is going to be compression properties. There are number of methods for finding out the compression strength and the modulus for a composite. Now usually the problem with any compression test is, if I have a compression specimen, say this is my compression specimen, and I try to apply compressive force in this particular direction, it is going to buckle. And then if it is going to buckle, I am not going to get the results of pure compression. I do not want that. I want the results of pure compression. So all the test methods which are designed for checking the compressive properties should always take into consideration the fact that the gauge length has to be such that of the sample that there is going to be no buckling at all, and I am going to get pure compressive properties. So then IITR is one of the methods that has been designed for finding out the compressive properties. So now here you see the specimen of a specific length, that is 165 mm. I have the edges tabbed at a very large length here on both the sides, and I have a 12.7 mm gauge length. So as I mentioned earlier, this gauge length, why this value of gauge length? So that I want pure compression in this region. I do not want any buckling taking place in this particular region. So basically this test was first carried out in Illinois Institute of Technology Research. So because it was carried out in that particular institute, this particular name has been given to this test. So now what does the basic test sample and the fixture consists of? So it consists of wedge shaped grips. So you can see that these are wedge shaped grips. They fit into a fixture which is straight sided here. So these are wedge grips put into both these fixtures. Now these wedge grips are important for self-aligning of the sample. So along with these wedged grips, what I have is I have this guiding pins over here. These guiding pins are there in the bottom half. They slide into the ball bearings which are there here into the top half, so that during the testing the alignment between the two halves of the fixture remains proper. There is no buckling that is going to take place. Now this wedge shaped structure is going to ensure that the two halves here remain perfectly aligned, and in this particular space I am going to experience the sample is going to experience pure compression. So once this sample is loaded here, compressive load is given in this particular direction, and then the compressive modulus and the compressive strength is found out. Now, as in case of your tensile specimen also, I have these end tabs, and these end tabs are again adhesively bonded here. Now, always remember that whenever there is going to be this adhesive bonding over here, there is going to be stress transfer taking place from these particular grips to the sample through this particular adhesive bond over here. So, and it also has to be such that there is no crushing of this particular sample in the grip over there. So now the maximum load that can be transmitted due to shear through this controlled through the tabs is controlled by the shear strength of the adhesive and the interlaminar shear strength of the tab and the specimen material and the total tabbed area. So naturally then the maximum loading becomes a function of the type of adhesive that you are using here. Now if I go to the next test, compression test, so it is sandwich edgewise compressive test. Now how is this test designed and how is this test specimen designed? So you can see that I have two composite specimens here. Now these two composite specimens are naturally made of the different laminas. I have a laminate here. Now in between this, what I have is a honeycomb. This honeycomb is made out of aluminum. So this is a lightweight honeycomb. On both the sides of this lightweight honeycomb, what I have is the end caps. Now basically, what is the function of the honeycomb? The function of this honeycomb actually is to prevent any buckling that is going to take place in the sample. Why are the end caps added here? The end caps are added for supporting the specimen and preventing any crushing of the specimen that is going to take place. So what I have is two straight sided specimens. which are bonded to the honeycomb, end caps placed here, and the compressive load applied. So now, what are the key features about any compressive test? So metals usually are ductile. Generally for metals, the tensile as well as the compressive moduli are equal. But in case of composites, specifically if I have a 0-degree laminate, then the tensile and compressive moduli are not equal. Then unlike your normal metal tensile stress strain curves, compressive curves for composites may not always be linear. Now the longitudinal compressive strength of a 0-degree laminate depends on fiber type, fiber volume fraction, matrix yield strength, fiber L by D ratio, how straight is the fiber, how well aligned is the fiber, and also very importantly the fiber matrix interfacial shear strength. So as I said, inherently composites being inhomogeneous, all these factors come into consideration when I am going to find out their compressive strength. Now, amongst all the fibers which are available, Kevlar, you know what Kevlar fibers, you know that Kevlar fibers are bulletproof, etc. So the compressive strength and the Kevlar fibers for these reinforced composites, in this case, the tensile strength is much higher than the compressive strength. Also, but in case of carbon fiber and glass fibers, the compressive strength is only slightly lower than the tensile strength and the modulus. While as in case of boron fibers, there is no difference in the tensile and the compressive strength. So as I said, because composites are inhomogeneous, you cannot make any blanket statement about them. They are like, therefore, like unlike the metal, their tensile and compressive strengths are not going to be equal. Also, unlike metals, their compressive strengths are not going to be, or their stress strain curve is not going to be linear. Now here clearly it is seen that fiber type is going to make a lot of difference in correlation between the tensile and the compressive properties. So for Kevlar, the tensile properties are much better than what the compressive properties are. For glass and boron, they are very close to each other, but sorry, for glass and carbon, they are very close to each other, but for boron, they are almost the same. So we have to remember very importantly fiber type and fiber volume play a very important role along with the matrix. So these were the key points about compressive properties. Now the next very important property which is there for laminates or for composites are the shear properties. Till now, I have characterized my lamina and I have found out E1, E2, I have found out mu12, I have found out mu21. All of this I have found out by using tensile properties. Also, I have tried to know how to find out the longitudinal tensile strength and the transverse tensile strength. Compressive properties, yes, using the IITRI fixture or the edgewise compression test, I am going to do the compressive properties. Now, the next important property which I need for characterizing of a particular lamina or a laminate is the G12, which is the in-plane shear modulus. So I need to find out in-plane shear strength and I need to find out in-plane shear modulus. So here there are number of tests which are used to do that. The first test that is used to find out the shear properties is the plus minus 45 coupon test. Now what I have is, as it is shown in this particular figure, I have a laminate built up, a symmetric laminate built up of plus and minus 45 angle laminas. Now on this, I have got two strain gauges, one to determine the modulus in this direction, say X, the other to determine the strain in the direction Y. Now what is done in this particular test is, to this lamina is placed in a tensile testing machine and it is being pulled in this particular direction. The property that I get actually is not, so whatever reading I get from the tension test is not the shear moduli or the shear stress or the shear strain I'm going to get. I get what is called as the off axis tensile properties, and from the off axis tensile strength, so which is sigma x, I want to find out tau xy. From that I want to find out tau 6. From that I want to find out gamma 6, and from the same I want to find out G12. So I carry out this tensile test of a lamina or a laminate which is plus or minus 45. I put in the strain gauges. So what this measures is sigma x. So doing my micromechanics and doing my macromechanics and some trigonometry and transformations, I find out the value of tau xy, and I find out the value of tau 6 from this particular test from sigma x. I find out gamma 6 from epsilon x and epsilon y, so which is measured by the strain gauges. So strain in the x direction and strain in the y direction. From that I get the shear strain, and then using this particular formulae I get the value of G12. So this test, I'm not generating pure shear. It is not very easy to generate pure shear. I am using your off-axis test and relying on generation of shear properties here. And then through my understanding of macromechanics, I'm trying to find out the value of tau and G12. So now this value of modulus that I find out of tau is not affected by the edge effects present in the specimen, or it's not affected by the biaxial state of stress, because here there is going to be a biaxial state of stress existing because I have a plus minus 45 lamina and I am applying the load in this particular direction. But the problem with this test is it overestimates the in-plane shear strength of the lamina. And in estimating this strength, it does not take into account the edge effects or the influence of other stress components in this lamina. So basically, this is not where I get pure shear. I use my macromechanics knowledge to find out the value of pure shear. Now, similarly, I do one more test, which is again a off-axis tension test, which I do. Again, I make a lamina wherein this lamina I make then with a 10-degree fiber angle. I put on two strain gauges here, A and B at 45 degrees. Now what I measure is I am going to measure sigma x and I am going to measure strain here. So here you can see the strain gauge rosette, and from that I am going to get the value. So gamma 6 is nothing but the shear strain. That is going to be the difference in the strain measured by the strain gauge A and the strain gauge B. And what is going to be tau 6? Tau 6, I am going to now use my trigonometry and transformation. And from that trigonometry and transformation, I am going to get the value of tau 6. And I know that in this case, theta is 10 degrees. To this, I apply the Tsai-Hill criteria of failure. You have already studied the criteria of failure to get the value of F6 in terms of sigma 1 and F1. And using the Tsai-Wu criteria, I get, also using the Tsai-Wu criteria, this is the value I get here. So basically, in this test method, the effects of longitudinal and transverse stress component, that is the two biaxial stress components on shear response is seen. The specimen usually is going to be a 6-ply specimen. Again, end-tabbed always in both the specimen, the previous plus minus 45 and also in this specimen. Because it is a tensile test only that I am doing, there has to be end tapping so that there is no crushing there in between. So again, both these tests are not direct shear tests, but I am using the fact that With a off-axis tensile test, I can find out the shear properties using transformations. There is one more test which is called as a 3-rail shear test, and also there is a 2-rail shear test. Now the difference between the 3-rail and the 2-rail shear test is, in case of 2-rail shear test, what I have is a sample, a rectangular sample, and here I have 1, 2 and 3 rails, or these are the 3 what you can say fixtures in which I am going to bolt the specimen. In a 2-rail, only 2 rectangular tabs I have and I bolt the specimen. In the 3-rail, I have got 3 tabs that I bolt in the specimen into. So what is done is a compressive load is applied. Now when you see that this compressive load is applied here, naturally these are going to be the faces or edges where the sample is going to experience shear. So then how will I find out shear? I am applying load P. Due to this load P, the area is nothing but the length of the sample, the length here into the width, which is in the perpendicular direction to the board or to this particular slide. B is the perpendicular direction. So that is the area which is undergoing shear because of this P compressive force. So I'm trying to come close to create pure shear condition. So these are going to act as restrictions, and these are going to sort of cause shearing at this surface and shearing at this particular surface, these two surfaces. And that is why it is 2LH in the denominators. So I come close to trying to, mimic what is the pure shear condition. So that coming close to directly reading of properties which are going to be shear properties. So from this, I get tau 6 as P upon 2LH and gamma 6 as 2 epsilon x. Now, from where do I measure this? I measure this from putting in 2 strain gauges which are placed at an angle of 45 degrees. So this is in detail about the 3-rail shear method. The next method that I'm going to discuss here is, this method comes very close to applying pure shear. So if I see this figure, what I have is, I have a sample which has got a double notch. Now, we know very well that when I create a notch anywhere, I create area of stress concentration. So what I have done is, with these notches, here this is my gauge length, and here I have created the area of stress concentration. So you can see this W, this is sort of my gauge length, and I have tried to create an area of stress concentration. So what I have done is, this is something I can say similar to a 3-point bending or a 4-point bending. So I have supports which are added here, and I'm trying to push the specimen in this particular direction. So if you want to just see how the test is carried out, I will just share a video with you. So I'm trying to share a video with you right now. So can you see my screen? Can you see the screen?
Yes,
Where I'm trying.
ma'am, are you playing the video?
Yeah, I'll start with the video, but can you see the YouTube screen here?
Yeah, we can see.
Yeah. Now I started playing the video. Can you see it?
Yes, it is audible
Yeah.
also, and
Yeah. So see, this fixture is that particular fixture for ISOPSQ test. Now I have this double notched sample here. Now you can see that I have put it in a tensile testing machine, and here I will say that, say this particular C part of this fixture here is fixed, and this rest particularly here at this particular position, and it's being pushed in the downward direction. So this is the gauge area, and in this gauge area I am going to come to what is called as pure shear taking place here. Now this video is played at a faster rate because usually, as I told you, with compression specimens the rate of testing has to be very slow because of the rigid nature and less of ductility in these composites. So you can see that the specimen is being pushed here downwards, and you can see what is exactly happening in this gauge area. So basically, if I'll just replay the video again for the clearer understanding. So again, it is something similar to the whole setup or force balance is something similar to what happens in a flexural or a bending test in a tensile testing machine only. This half is kind of supporting the sample, while as this half is being pushed down so that shear is being created in this particular region over here. So when I push this down, naturally in this notch area, the material is going to be sheared, and then whatever I read off the gauge, the reading is going to give me the shear property. So this showed me the way in which I'm going to use this ISO-PESQ fixture. Now I'll share back my presentation. So ma'am, can you see the presentation?
Yes, ma'am. Yes.
Yeah. So then here is kind of the force and the what you can say, the force is acting here on the specimen that are shown over here. And here you can see that in this particular area, this is the shear force diagram. So in this particular area, you can see that there is a constant shear force that has been created here. So this is a typically SF and BM diagram that we use for understanding the beam bending. So I'm using a beam bending principle over here to create pure shear in this particular region. So this test is not relying on any off-axis tensile property and then doing the further mathematics and then getting the value of shear. But this test is relying on purely creation of shear in this particular area of over here. Of course, care has to be taken that in this notch, there have to be no sharp edges. There has to be a proper radius notched over here. So then the shear stress that is going to be generated here is the formula. Tau12 is going to be P upon WH, where W is the width and which is shown here, which is the gauge length, and H is going to be the thickness of the sample there. There are going to be two strain gauges which are going to be attached at plus and minus 45 in this particular gauge length, and that is going to tell me of the shear strain that is generated. So the gamma 12 is going to be epsilon plus 45 minus epsilon minus 45. So from this, I am going to get directly the values of tau 12 and G12. So this is called as a isopescu fixture. A particular scientist, Nikolai Isopescu, he developed this fixture, and with this double notched V specimen in 4-point bending, it helps in creating shear force in the gauge region, which we already saw. So this is the gauge region, and this is kind of a 4-point bending test that is generated. Now it is seen that close to the vicinity of the notches, a state of pure shear can be got there. Now these notches, naturally you know that they create areas of stress concentration. Now you need to have what you say a radius at the root of the notch over there. Also if there's going to be an increase in the orthotropy, meaning that E112 is going to be far greater than E22, also then at that time it's going to be an area of stress concentration there at the notch. So these notches, the specimens have notches which have a 90-degree angle, and the depth of the notch is 20% of the width of the specimen, and 1.3 mm is the radius of the root of the notch. So this is one of the tests which is going to give me pure shear condition as compared to the previous two tests of plus minus 45 and 10-degree specimen. With my 3-rail shear, also I am trying to generate pure shear in this particular area. So here also I can get directly the value of tau 16, but in these previous two tests, which are 10-degree off axis or which are plus or minus 45, I am not going to get pure shear. Through the tensile test, I am going to find out by applying my knowledge of macromechanics the shear G12 and tau 16. So now, as I said, there are types of tests which are flexural tests. Now these flexural are going to be 2-point bending or 3-point bending. So these examples, this will be called as a 3-point bending. This is a 2-point bending test. So naturally, you know that there are two supports on which the specimen is going to be placed. Now the specimen preparation, that is the length, the width and the thickness of the specimen is as per ASTM standards D790. But in this case, important is the span length, and that is determined by the thickness of the specimen. Now this test of flexural to 3-point or your 4-point bending, these values are nowhere going to be used for characterization of the lamina, but this is going to be a quality assurance test, like a quality assurance test or a screening test. So for that, I'm going to do the flexural test. Now the next important test which I will do in case of your composite laminas and laminates, especially laminates, is going to be the pin bearing test. So if I am going to use the laminates for generating structures, then for that I need to fasten, and if I am going to use mechanical fasteners, then naturally what I need to do is I need to bolt the various laminates together. So for doing that, holes are going to be drilled, and then I'm going to do the bolting, etc. So in order to understand the behavior of the laminate in such kind of conditions, I will carry out this test. So how will I carry out this test? A specimen which is going to be something similar to a square test or a rectangular specimen, and it has got a hole in it. This hole is for a pin. This is a steel pin. Okay. Now this is the specimen. One end of both the ends of the specimen are going to be placed in a tensile testing machine with this particular, the way this fixture is generated. So I have this fork. My sample is placed here and a pin is placed here, and then the fork is attached to one jaw of the tensile testing machine, and this specimen is going to be held in the other jaw. So naturally, when this specimen is going to be pulled at this particular point or this circle where the pin is going to be there, the failure is going to be somewhere here. This I'm trying to mimic as to what happens when there are going to be fasteners in the laminate over there. So then there can be different failure modes. Now there are two aspects on which the failure modes depend. One aspect on which failure mode depends is the geometry. So what is the geometry which affects the failure modes here? The geometry here is the width of the specimen, the distance E, that is between the center of this particular circle or the pinhole and this particular edge, and the diameter of this edge. So whatever is going to be the variation in geometry, no matter from which laminas is this particular specimen is going to be made, there's going to be a certain way of failure, and the other is dependent on the buildup of the particular laminate which is used to make this particular structure. So now there are different modes of failure in case of pin bearing. So here is a shear out failure wherein actually the spin is going to just kind of create forces such that there's going to be completely failure in this particular mode where the pin is just going to shear out the specimen. The second is where there is going to be a tensile failure, that is the specimen is going to break in this particular direction. So this is net tension. Here the specimen is going to kind of cleave off into two halves, or then for specimens which are ductile, there's just going to be some, what you can say, extension taking place slowly and surely, and there's going to be some ductile failure, or it is called as a bearing failure where there is the elongation of the hole. So these are the different kinds of failures. And then what are the different geometries? So if I have a low width if I have a low specimen width to this D ratio, meaning that the width is much lesser than this particular diameter, the material is going to fail by pure tension. And at a low E by D ratio, the material is going to fail by shear out failure, meaning that E is this distance. If distance is much lesser than this particular diameter, the specimen is going to shear out. Now the load carrying capacity of this laminate is low if either of these failure modes occurs instead of bearing failure. So bearing failure is naturally going to be not a sudden failure. These two failures are going to be sudden failures. And in case of bearing failures, there is going to be a warning like the ductile failure. So for bearing failure, what you need is naturally the width of the specimen has to be much more than the diameter of the hole, or the distance between the end of the specimen and the diameter of the hole has to be greater. So as I said, there are certain geometric conditions which decide the type of failure. And also there are some conditions which depend on the kind of layup of the laminate that is made, which is going to lead to the failure of pin bearing. But as I said that this test is going to be really a important application oriented test if I am going to use all of these laminates with mechanical fasteners. So that was about pin bearing test. Now next, I'm going to discuss a case. I'm going to discuss a case where, say, I have a laminate. Now by now you know what is a laminate. It is nothing but a stack of number of laminas. Now all these laminas are put together, and you know very well that there are certain assumptions in the classical lamination theory that between the laminas there is a non-shear deformable bond, which is very important, so that the failure is not going to be due to the interlaminar shear, but we are going to say that the failure is going to be due to the breaking of the fibers or the matrix reaching its ultimate strength values. So then when I tensile test a lamina, how does the failure take place of that particular lamina, and what is the algorithm of understanding the failure of the laminate, and when do I declare now that the laminate can no longer take up any load? So this ply by ply failure, if I need to understand, then what is the stepwise procedure? So first what I'm going to have is I'm going to apply the force onto the laminate. Also, I'm going to apply some moments. So the load is going to be applied in the form of force and moments. And the deformation due to this applied load is going to be due to mid-plane strains and curvature. This you have seen in the classical lamination theory. Then the load is increased till the first ply is going to fail. So this is termed as first ply failure. So then the laminate stresses are determined as a function of the load, first in the laminate coordinates, followed by those in the principal material directions. So this also you have seen when you, was covered in the lecture for classical lamination theory. Then the next step is the stress and the strains in each lamina are compared with the allowable values using the failure theory or failure criteria. Now this also has been mentioned in your previous lecture. So what are we trying to do? If I go back again, what are we trying to do? We are taking a laminate, which is a stack of number of laminas. Load is applied to this in terms of either force or moment. Then the deformation is in the form of mid-plane strains or curvature. Now, depending on the orientation of the lamina or the ply, here ply is nothing but a single lamina. Depending on the orientation of the lamina, whichever is going to be, say, a lamina which is weaker due to its particular orientation with respect to the load, it's going to fail first. So that is the first ply failure. Now stresses in the laminate are going to be, not the whole laminate due to the failure of this ply are going to first be seen in the laminate coordinates, then in the principal material directions. This is nothing but the transformation that we have studied. Now stress in each lamina is going to be, or strain is going to be predicted using the failure theories. Now failed ply has to be totally eliminated using the discount method, means that it has to be totally eliminated from any load bearing and is considered, or residual stresses are assigned to the failed lamina. So we should consider that this particular lamina no longer can bear any stress, and taking that into consideration, then the new stiffnesses have to be recalculated. So then new ABD matrix have to be recalculated. Now the lamina stresses are recalculated to determine their redistribution of this after this lamina has failed. So now imagine, say you have a 10 ply lamina. Say you have one lamina failed in that laminate. It had some load bearing capacity, and because of that lamina, it also contributed to the modulus. Now it is no longer going to contribute to any load bearing. So remove that lamina and then find out the ABD matrix. If no more lamina fail, then the load is further increased until the further lamina fails. And this keeps on continuing till I'm going to get the complete failure of the laminate. So this is an algorithm for whatever I have mentioned till now. That is the step ply by ply failure. So I start loading the laminate. Then I calculate the ABD. If there is no failed lamina, there is further increase in the load. Then find the lamina stresses per unit of load, apply the failure criteria, and calculate the load for the failure of the lamina. Once the lamina has failed, degrade that failed lamina and calculate the laminate deformations. Go back again, calculate the ABD further for that failed lamina, and then do the same thing again. Now, if the lamina doesn't fail, then find lamina stresses at last load level. Again, apply the failure criteria. Now, if no lamina fails, increase the load further. If lamina fails, then degrade that lamina. And if no lamina are left in this process, then the complete failure of that particular laminate has taken place. So basically, I have built my laminate taking into consideration my application. Therefore, I have laminas at certain orientation placed there. I'm also aware of the loading conditions, and therefore I have designed it to be, say, a completely symmetric laminate or anti-symmetric laminate depending on my requirement. And then this algorithm has been kind of calculated or analytically calculated or simulated, and then the experiment is actually carried out for testing of this particular laminate. So now if I take an example of this, I have a cross ply laminate. Now you know what is a cross ply laminate. It has got 0 and 90 degrees alternating plies there. Also, if I am going to say having n identical layers of which L have fibers which are in the loading direction, M have transverse layers with transverse loading. So now I have ET as the longitudinal moduli, which is synonymous to E1. I have EL synonymous to E1 and ET synonymous to E2. Then the limiting strains epsilon LU is nothing but the epsilon 1 and epsilon TU is nothing but epsilon 2. Now suppose I am going to apply the load in the direction of the fibers, that is the longitudinal direction. Naturally, I know very well that the plies which are exactly 90 degrees are going to fail first because they are weak in that particular direction. So if this is going to be my structure, then I know that I use the rule of mixtures, and this is the weighted proportion in which the lamina are going to contribute to the laminate modulus. So I have L by N longitudinal plies, I have M by N transverse plies, and in that proportion they are going to add to E or contribute to E. This E is the total modulus of the complete laminate. Now this modulus is valid till all the plies are intact. Remember that very well. This is till none of the plies have failed till now. So now the composite stress at failure for 90 ply then, because we know that the 90 degree are going to be the ones which are going to fail. So suppose the first or all my 90 degrees plies have failed, then the stress at failure of this 90 is going to be E into epsilon T, where epsilon T is the strain in the 90 degrees plies. So now the entire load has to be taken up by the 0 degree plies, because I have come up to a point that the 90 degrees plies have completely failed, and therefore I have to recalculate my modulus, and now my modulus is only going to be L by N, because there are L longitudinal plies in the total N number of plies, and they constitute the complete now the modulus of the lamina after the failure of 90 degrees plies. Now ES is nothing but the secondary composite modulus, which is equal to the modulus of 0 degrees plies corrected. Now naturally there is some reduction in area taking place because all my 90 degrees have failed. So now I have the new now the new composite strength, and when will my composite now finally fail? My composite is going to fail when my 0 degrees all the 0 degree laminas in that are going to fail. So naturally sigma A is the stress in the 90 degrees ply which already is there. In addition to that, I have this particular stress, which is ES is the recalculated modulus, which is only that of the 0 degrees plies, and this is the strain. Now this is nothing but the difference in the longitudinal and the transverse strain, because already there is failure of this taken place. So that strain has to be removed from this particular strain value. So if I go to this particular diagram, and if I try to explain from this, here I begin for the complete laminate. At this knee, all my 90 degrees plies have failed. So because all my 90 degrees plies have failed over here, the stress here is sigma A, failure of all 90 degrees plies. After this, it's a bilinear plot. So this is in initial linear region where both my 0, 90 were intact. Here the 90 have failed. Now complete load is taken up by 0 degree splice. They will remain taking the load until, naturally, where we have seen in our micromechanics, first there is going to be the failure of the matrix that is taking place. So at sigma m stress, the matrix has failed, and then here finally I am reaching the ultimate failure strength of the fibers, and this is the point where the complete laminate has failed. So this initial part, it is going to be the failure of 90 degree splice. Then complete load is taken by 0 degree splice up to this level where there is a failure of matrix, but still the fibers keep on taking the load. This is the ultimate failure strain of the load, and therefore the ultimate failure strength of that particular laminate. So this is, I have explained it to you graphically, and these are the terms which are, as I said, numerically put in here. So now then, EE is going to be the effective modulus, and this effective modulus is naturally going to be the combination of this particular moduli. So this is the total moduli when all the plies were intact. This is the moduli when 90 degrees plies broke off. This is the stress at the knee minus, or sorry, not minus, divided by the stress at failure. So this is an example of ply by ply analysis of a cross ply laminate, and this can be carried out, and this can be measured by a normal tensile test carried out on the lamina. So here I end my lecture. So just a recap of what we have actually done in this lecture. So if I just highlight what has been done is, why do we need to characterize the composites? We need to characterize the composites because we need to find out E11, E22, G12 and mu12. These are found out by tensile tests. We need to find out the strength. G12 is found out by shear test. So we saw two types of compression test, four types of shear test. Also, there are some tests, as I mentioned. Those tests are screening tests, which are 3-point bending. And there are some tests which are application oriented tests, like the pin bearing test. So this was, as I said, from this pyramid, we are at this base level where we have used different test specimen to characterize the lamina and to characterize laminates. We have still not gone in the regime of laminates, then the regime of structural elements like beam and the final structures. So I would like to thank you for your patient hearing. And also I would like to thank the organizers for giving me this opportunity to talk to all of you.
Thank you, ma'am. Thank you. It was a very nice presentation covering the topics like need for characterization of composites and various properties related to composites like tensile, compressive, shear, pin bearing. Everything
Yes.
was very nicely explained, ma'am. It was a pleasure hearing
Thank
you.
you, ma'am. Thank you.
Uh,
Thank you for inviting me.
Now unmute the participants and they can ask questions one by one. There are also some questions in the chat box. So,
Yes.
Mr.
Mm,
Suraj, there are some questions in the chat box. I will ask you them first.
okay.
Just a moment. Uh, okay. One
I can't
question.
see the questions in the chat box actually.
Okay. Um,
I don't know why I can't see them.
No, one question is that in case of 3-point flexural test, when
Yeah.
do we stop applying the external load?
Yeah.
Do
So
we?
basically,
Yeah.
so basically in a 3-point bending test, the failure is considered where we know in a 3-point bending test, the outer fiber of the sample is always in tension and the inner fiber is in compression. So when the outer fiber fails in tension, we consider that load and that deformation as the failure load and deformation in a 3-point bending or in a flexural test.
Okay, ma'am. Then the next question is, considering ASTM or ISO code for flexural test for plastics and FRP composites will be followed?
Actually, see, the D790 is only the test method which is usually followed. Now, this D790 method is followed for our plastics also and for composites. But if you go into details of that method, then for a composite, they have properly mentioned the span that is between the two supports, which is related to the thickness of the composite. So we will have to make the sample as per that particular standard. So there are certain values. Offhand, I'm not being able to exactly quote those values, that if the span is say this much mm, I mean if the thickness is say 10 mm, what should be the span, but they have been given in D790 standard.
Okay, ma'am.
Mr.
One more
Akash?
question.
Mr.
Yeah.
Akash?
Yeah. Hit, ma'am, continue.
I can't hear. I didn't hear the question actually.
Ma'am, the question is by Akash Gupta.
Huh?
Is there any test based in fatigue loading?
Yeah, there are fatigue tests. Actually, due to a paucity of time, I have not covered the tests in fatigue loading. But there are tests which are available in fatigue loading. So then the test method, if we can note down, then the test method is D3479. ASTM D3479, which is tension fatigue for composites.
Okay, ma'am. And the same
Hello,
question.
ma'am. Am I audible?
Yeah, yeah. Akash, are you there?
Yeah, yeah. Good evening, ma'am. My name is Akash Gupta.
Yeah.
Actually, as I asked, because like fatigue loading test is there, ma'am. Is there any theory of failure that failure criteria is also a different, or is the same criteria basically we use?
So basically for fatigue loading, uh, I am not exactly aware of a failure theory or failure criteria which is separate than what we use for normal fatigue failure. So we use an SN curve for that, right? For metals and other plastics. So I'm not exactly aware of any other specific criteria for fiber reinforced composites.
Okay, ma'am. One more question I have.
Yeah,
Ma'am, you're actually talking about the ply-by-ply laminate failure.
yeah,
Is it a
yeah.
same approach as like a progressive damage analysis approach?
Something similar to that. See, basically, when I was talking about 090 or a cross ply is a classic case because it is easy to understand, because we very well know that the 90 are, if I am going to apply load in the longitudinal direction, the 90 plies are the ones which are going to be weaker and which are going to fail first. So naturally, initially, what I'm going to do is I'm going to eliminate the load carrying capacity of the 90 once they fail and then calculate. So this is similar to progressive damage. Yes.
Thank you, ma'am.
Good evening, ma'am.
Yeah.
Myself Madhavan from Anna University, ma'am. Uh, Ma'am, I had two doubts. Is it
Yes.
audible, ma'am? Ma'am,
Yes.
from this lecture and my previous work, there is for composite laminates, that is fiber reinforced laminates, the classical laminate theory and the numerical modeling is suitable for only on angle ply, cross ply, and then unidirectional laminates alone. But is there any numerical or mathematical model for non-woven composites, ma'am, like a short fiber or continuous fiber in random oriented fiber?
Yes, yes, yes. Uh, Right now, actually, I'm not very aware, but I will answer this question for short. I am also not aware of any numerical method for these particular short fibers or randomly oriented fibers.
Okay, ma'am.
There is a simulation software called as Sysply, but then again, that is not for randomly oriented. That is also for woven and these kind of fibers.
Okay, ma'am. Is that testing the ASTM standards, ma'am, for unidirectionals like ASTM D3039,
Yeah,
D790, and 5379 for shear, isoprecious shear, and
yeah,
double V shear?
yeah.
For that the same standards could be followed for a random and bidirectional or multidirectional
See,
laminate.
no, I don't think the same standards can be followed for random or bidirectional. So they come closer to we can if it's a particulate composite, I can get it closer to your
No,
kind
ma'am,
of
it's a
homogeneous
fiber
sample.
only, ma'am. Fiber only, ma'am.
Oh,
That is a
fiber,
non-woven,
yeah,
soft strand
non,
fiber mat, ma'am.
but random fibers,
Yes, ma'am. Full level
soft
random,
strand and
but
random.
here and another one is bidirectional. That is 090 or a oven rowan mat.
No, then I will go in for these D3039 only for that.
Oh, okay, ma'am. But same standard only. We have to
Yes,
choose one for
yes,
both materials. Okay,
yes.
ma'am. And one more thing, ma'am. For isoprecious shear, we have to hold the samples with less width, but the same standard that is modified shear double V shear is also some researchers are using, where the width is somewhat increased and the length of the sample should be reduced.
Yeah, because see, all of this, the focus here, all of this is to create pure shear in that particular W region.
Okay, ma'am.
So in that particular W region, see, we do not want any moment or we do not want any tensile load over there. We want a
A
pure
compression
shear
load, that is
being compression load and a
compression load.
pure shear being generated in that region. For that
Yes,
reason,
yes, yes,
these
ma'am.
things have to be
So
taken care
both
of.
the tests are also acceptable only, not
Yes.
the ISO species is not for not acceptable for some other
See,
cases.
those
And
are variations of these ISO-PESQ.
okay, yeah, yes, ma'am. That is developed one of a double V share from isoprecious only. The samples only different, sample size only
So
different, ma'am.
then, see, basically our focus has to be in the width region where the
Yes, ma'am.
failure has to take place in the region, but not anywhere close to the notch. So
Okay, ma'am.
that is the main focus which has to be there when I'm going to report the strength of the sample.
Okay, okay, ma'am. Thank you, ma'am.
Thank you, ma'am,
Yes.
for this session.
Thank
Uh,
you, ma'am.
the department is highly thankful to have you as professor in this
Yes,
session.
yes. I am thankful to you too for giving me this opportunity. Thank you.
Thank you so much, ma'am.
Yeah.
Ma'am,
Yes.
someone is asking about the software you have
Yeah.
suggested. So,
Yeah, I just saw it. Uh,
can you repeat,
what
ma'am?
is the software used? What is the software used? Somebody named Sam, a participant named Sam, is asking what is the software used. I think Deepti ma'am is not in the line. She is not present. Okay, for the participants, the one announcement has to be made. The presentations and videos are now available on MS Team in the files which have already been uploaded. So you can access those from directly from there. Up till now, the presentations and the videos have been uploaded there. That will be helpful for your preparation during the exam. And tomorrow we'll be starting the session.